Hello viewers, my name is Dr. Ajay, Associate Professor, Department of ECE, Institute of Aeronautical Engineering College, Hyderabad. Today we are going to discuss the topic on a discussion of tutorial question bank of the course Antennas, Waves and Propagation. The Model 5 question bank we are going to discuss today. So the Model 5 belongs to the radio wave propagation. Let us see the problem solving and critical thinking questions on the radio wave propagation, which belongs to the course Antennas, Waves and Propagation. So let us start our session today. Derive the field strength equation at a distance in space wave propagation. So derive the field strength equation at a distance in the space wave propagation. So here the field strength is the amount of field electromagnetic energy received at the receiving antenna. So let us denote it by the symbol E, R. Let us denote it by the symbol E and R here. So E R represents the total electric field strength received at the receiver. So here let us calculate the electric field strength. Let us derive the expression in space wave propagation. So let us assume here there is a transmitting antenna. Here there is a transmitting antenna here. And here there is a receiving antenna here. Whose heights are height of the transmitting antenna HT. And this is the height of the receiving antenna. And here there is a transmission path here, direct path here. So this we call it as a D1. The distance is the D1 here. Assume this as a T dash, this is as R dash, and here this is the T, and this is this R point here. So this is the surface of the earth here. Let us assume this as the surface of the earth to be flat here. And whenever the signal is being transmitted, there will be a direct path for T dash, R dash, represent as D1. And sometimes the electromagnetic rays will touch the surface of the earth and reflect back to the receiving antenna. Let us assume this as path D2 here. This as D2 here. So this is the path D2. We can represent as G2 here. And let us assume here, extend this path here. And also extend this path here, or this both intersect at this point here. Assume this as A. And draw a line parallel to TR. And join these 2 points here. Assume this as B here. Now this distance between the transmitting antenna and receiving antenna is D here. And join these 2 points here. Draw a parallel line here. Assume this as M dash. And this has height of the transmitting antenna. And this has the height of the receiving antenna here. And this is the mirror image. So this is also the HR up to A. So these are the notations we have used in our derivation. D1 is the direct path, D2 is the indirect path. And whenever you transmit the signal from the transmitting antenna, it is going to reach the receiving antenna in 2 different paths, D1 and D2. Hence the path difference, there is some delay. This delay is denoted by D2 minus D1 here. There is some delay in reaching the signals between the 2 paths. Why? Because the D1 path is very near to the R dash and D2 path is very far, and hence the D2 electromagnetic ray in this path, in the D2 path, that is T dash O R dash, it is going to reach to the receiver after some small finite delay. So hence there will be some path difference between the D1 and D2, which is indicated as a D2 minus D1. Now the phase angle. Now there is a path difference, definitely there will be a phase angle. So let us assume the phase angle as alpha here. So alpha is equal to 2 pi by lambda into path difference here. So this is equal to 2 pi by lambda into D here. So let us find out the value of D here. Now here let us assume T dash, R dash, here T dash, R dash and M dash. We want to find out the value of D1 first. So to find out the value of D1, assume the triangle T dash, R dash and M dash. T dash, R dash and M dash. So from this triangle, you can apply the Pythagoras theorem. Based upon the Pythagoras theorem, you will get D1 square is equal to HT minus HR whole square plus D square. So d1 square is equal to ht minus hr whole square plus d square. So for this triangle t dash r dash m dash. Similarly, to find out the value of d2, you can use the formula t dash a and b triangle. Now d2 square is equal to so we get here ht plus hr whole square plus d square. Now from these two equations, you find the value of d1, you find the value of d2, and based upon these two values, you need to find out the value of d. Now let us take this as 1 and this as 2. So d1 square equation let us assume as 1 and d2 square equation let us assume as 2. Now let us take equation 1 here and simplify here. So here d1 square is equal to, we are getting here d1 square is equal to ht minus hr whole square plus d square. So d1 is equal to ht minus hr whole square plus d square whole power half here. Now let us, from this equation, let us take d square common. So if you take d square common, you will get 1 plus ht minus hr by d whole square whole power 1 by 2. Again, d square whole power half is equal to, you will get d. So d into, so from this equation we can also write 1 plus ht minus hr by d whole square whole power half. So 1 plus x whole power n whole power, according to binomial expansion, we know that 1 plus nx plus n square x square and so on. So from this binomial theorem, we will get d into 1 plus half into ht minus hr by d whole square plus and so on. And we are going to ignore the higher order terms. Power 3 and power 4 and power 5. Why? Because the heights of the transmitting antenna will be very less when compared to the distance between the transmitting antenna and the receiving antenna. So the distance will be measured in kilometers, but the height of the transmitting antenna and receiving antenna will be in meters. So when we divide the meters with kilometers, we will get the lower value. So as the power increases, this value becomes almost to zero, near to zero. Hence, the higher order terms are ignored. So based upon this, you can write the d1 value as d1 is equal to d plus ht minus hr whole square by 2d. So similarly, you can also use the d2 value. So you can also find out the d2. So similarly, if you find out d2, you will get d1 is equal to d plus ht plus hr whole square by 2d. So we got d1 and we got d2. So d is equal to d2 minus d1. So if we simplify d2 minus d1, you will get 4 ht hr by 2d. 4 ht hr by 2d. If you simplify here, you will get 2 ht hr by d here. So this we got as d here. So what is alpha here? 2 pi by lambda into path difference. So here 2 pi by lambda into 2 into ht hr by d. So this you will get 4 pi ht hr by d lambda. This is alpha. So here this is the phase angle due to the path difference. So we are having another phase angle known as beta. So beta is 180 degrees, where theta is equal to alpha plus beta here. So theta is known as the total phase angle. The total phase angle depends upon two factors. One is due to the path difference. The other one is beta due to the ground reflected wave. Which is taken as 180 degrees. So theta is equal to alpha plus beta, where beta is equal to 180, the ground reflected wave. Now ER. Now we have to find out the ER value, the electric field strength reached at the receiver, which is given by the equation ER is equal to E naught into 1 plus K e power minus j theta, where theta is the total phase angle. Now if you calculate the value of mod ER, we take the model of mod ER. Let us take the value of ER. 1 plus k into e power minus j theta is equal to cos theta minus j sin theta. Now let us split the real and imaginary parts. 1 plus k cos theta minus jk sin theta. So this is the form of a plus jb. So if we take the modulus root of a square plus b square, you will get. So if we take the modulus of ER, you will get E naught into root of a square 1 plus k cos theta whole square plus k sin theta whole square we will get. So if we further simplify, you will get here E naught into root of 1 plus k square plus 2k cos theta. 2k cos theta. So again you can substitute cos theta. So 2 cos theta, cos theta is equal to 2 cos square theta by 2 minus 1. Root of 1 plus k square plus 2k into 2 cos square theta by 2 minus 1. Now k is the efficiency factor which is taken as 1. So when there are no losses between the transmitting and the receiving antenna, the efficiency factor is taken as 1. And what is theta by 2? So what is theta? Alpha plus beta. Theta by 2 is equal to alpha plus beta is 180 by 2. Now what is cos theta by 2 here? Cos 90 plus alpha here. So cos 90 plus alpha is equal to minus sin alpha. So cos theta by 2 is equal to minus sin alpha here we will get. So this will get simplified here. 1 plus 2 into 1, k is equal to 1. So 2 cos square theta by 2 minus 1. So if you simplify here, 2 plus, you will get 2 plus 4 cos square theta by 2 minus 2. Minus 2 minus get cancelled. So you will get 2 cos theta by 2. You will get 2 cos theta by 2. So you will get overall mod ER is equal to 2 cos theta by 2 into E naught. So what is cos theta by 2? So cos theta by 2 is nothing but 2, we got sine 4 pi ht hr by 2d lambda. Now d is far greater than ht and hr here. So we can write sine theta is equal to theta. So under this condition, mod ER is equal to 2 E naught into 4 pi ht hr by 2d lambda. But there is a relationship between the ground wave field strength and the electric field strength at a unit distance from the transmitting antenna, which is given by E naught is equal to EF by D and EF is equal to 7 root P. So if we substitute this here, you will get E naught is equal to 7 root P by D. Now let us substitute this E naught value in this equation. You will get mod ER is equal to 2 into 7 root P by D into 4 pi ht hr by 2d lambda. So you will get 2 to get cancelled here. If you simplify this, you will get 87.17 root P ht hr by d square lambda by d square lambda. So which is approximately equal to ER mod ER is equal to 88 root P ht hr by lambda d square by lambda d square here. So this is the derivation we are having. Let E naught be the field distance directed at R. The reflection coefficient at the ground is K. The magnitude of the ground reflected wave is K E naught. The two rays combine receiving point vectorially. So this is the derivation just now we have seen. We have final values of D1 and D2. And D2 minus D1, the path difference we are getting here. And the phase difference, alpha depends upon the path difference, which is given by beta into path difference. So if we simplify, we get the value of alpha here. Similarly, the resultant field strength at receiving point R is given by This general expression E naught into 1 plus k e power minus j theta. So after simplifying, you will get minus sin alpha by 2. But as we are calculating the modulus, so this becomes positive plus sin alpha by 2. Next, a pulse radio transmitter operating at a frequency of 1.69 megahertz is required to provide a ground wave having a strength of 0.5 millivolts per meter at a distance of 16 kilometers. The transmitting antenna with an efficiency of 50% produces a radiation field proportional to cos theta. The ground wave sigma is equal to 5 to 10 power minus 2 ohm per meter. Epsilon r is equal to 15 here. And calculate the power transmitted. So calculate the power transmitted. So all the data is given. So EG value is given as the ground wave field strength 0.5 10 power minus 3. The frequency is given as 1.69 megahertz. D, the distance is given as 16 kilometers. The efficiency is written as 50%. The efficiency is given as 50%. So from this frequency, you can write lambda is equal to C by F. 3 into 10 power 8 divided by, so 1.69 into 10 power 6. So this is equal to 177. We'll get. Now, we need to know whether the antenna is vertically polarized or horizontally polarized. So here, so when the antenna is vertically polarized, the formulas are different. And for vertically polarization antenna, so in the problem it is given as cos theta. So the radiation is maximum in the direction of cos theta. So when we can say the radiation is maximum in cos theta. So whenever the antenna is vertical, the radiation will be perpendicular. The radiation will be perpendicular. It means theta is equal to 0 and theta is equal to 180. The maximum radiation is we are getting here. So the radiation is maximum either in theta is equal to 0 and theta is 180. So for this theta is equal to 0 and theta is 180, so we are taking the function as cos theta. So when theta is equal to 0, you will get maximum here. When theta is equal to 180, you will get 1 here. So when 0 and 180, the magnitude of the cos theta function becomes positive 1. Hence, we can assume that the antenna is being vertically polarized. So for vertically polarized antenna, the formulas are B is equal to tan inverse of epsilon r plus 1 by x. So what is the value of epsilon r given here? Given data. So here tan inverse of epsilon r. So epsilon r is nothing but it is given as 15. So 15 plus 1 by x is given by 1.8 into 10 power 4 sigma by f. So here 1.8 into 10 power 4, the value of sigma is given as the conductivity. It is given as 0.5 into 5 into 10 power minus 3. It is given as 5 into 10 power minus 3 here, sigma value. So here you will get 5 into 10 power minus 3 divided by f value is given as 1.69. So this if you simplify, you will get 53.6.2 mho per meter. So this is the value of x. So substitute this value of x here. You will get 53.2. If you substitute this here, you will get 16.72 degrees. You will get 16.72 degrees here. Now similarly, you can find out the value of P here. P is equal to pi by x d by lambda cos b. So pi by the value of x is 53.2. D, the distance is given as 16 kilometers. 16 to 10 power 3. Lambda is 177.5. Cos 16.72. So if you simplify it, you will get 5.09. Now what is the value of A here? So A is equal to 2 plus 0.3p. Formula is 2 plus p plus 0.6 p square. Now substitute this value here. Substitute this value here. You will get the value of A as 0.155. 0.155. Now we are having an equation to find out Eg is equal to E naught A by D here. and this equal to 300 root PR into A by D here. So this equal to EG is given as what? 0.5 into 10 power minus 3. This equal to 300 root PR. The value of A is 0.155 divided by 16 into 10 power 3. 16 into 10 power 3. So from this we can find out the value of PR. From this we can find out the value of PR. You will get 0.03 watts. Now this is the amount of power received for 0.03 watts. Now in the problem it is given as efficiency is equal to 50% only. The transmitting current efficiency is 50%. Hence efficiency is given as PR by PT is equal to efficiency. What is efficiency here? PR, we got PR as 0.03 by power transmitted is equal to 50 by 100. This one's 2. So PT is equal to 0.06 watts here. So 0.06 watts here. So this is the amount of power transmitted of the given data here. So this is the problem we are having here. Now derive the relationship between the maximum visible frequency and the skip distance. And here we know that the value of mu is equal to sin theta I by sin theta R. So this is equal to root of 1 minus 81 n by f square. So 1 minus 81 n by f square here. So here for angle for MUF, the highest frequency at which a wave is returned to the earth for a fixed distance of propagation, we call it as the maximum visible frequency, which is given as this happens only when theta r is equal to 90. Theta r is equal to 90. So theta r is 90 means you'll get the value as 1 here. Hence sin theta I is equal to root of 1 minus 81 n max by f square MUF. So Fc is equal to 9 root n max. So Fc square is equal to 81 nm. Substitute this value here. So we will get sin theta I is equal to root of 1 minus Fc square by f square MUF. So this is equal to 1 minus Fc by f MUF whole square. So if you simplify squaring on both sides, you will get f MUF is equal to Fc secant theta I. F MUF is equal to Fc secant theta I. This is known as the secant law. This is known as the secant law. And the relationship between the MUF and skip distance is given by D is equal to F MUF is equal to Fc into root of 1 plus D by 2h whole square. F MUF is equal to Fc into root of 1 plus D by 2h whole square. So this is the relationship between the maximum usable frequency and the skip distance. A communication link is to be established between two stations which are 1500 km apart. The maximum usable frequency chosen is 37.95 MHz. Calculate the critical frequency in megahertz. So calculate the critical frequency in megahertz. So what is the given data here? The frequency is given 37.95 into 10 power 6 and the distance d is equal to 1500 kilometers. We need to find out the critical frequency and the h is given 250 kilometers. 250 kilometers it is given the data. So here according to the problem we are having the formula f MUF is equal to Fc into root of d by 2h whole square plus 1. So f MUF is given as 37.95 into 10 power 6 is equal to Fc into root of what is the value of d. So we need to find out the value of Fc. So d is given as 1500 kilometers divided by 250 whole square 2 into plus 1. So Fc into root of 1500 by 2 into 250 whole square plus 1. So if we simplify this, you will get by 2 megahertz approximately you get 11.95 megahertz. So this is rounded up to 12 megahertz. So this is the critical frequency. So this is the given distance of propagation, 1500 kilometers. The height of the ionosphere is 250 kilometers. The Mach value is 37.95 megahertz. So Fc is equal to 12 megahertz. Fc is equal to 12 megahertz. It is required to establish a shortwave communication between 2 points on surface separated by 200 kilometers. Calculate a MUF, an angle of takeoff transmitted away from the following data. The highest signal frequency F MUF is the critical frequency is given as 7.2, and the virtual height of ionization layer is 200 kilometers. Assume the surface of that to be flat here. So here, according to the data given, what is D here? D is 1200 kilometers. H is 200 kilometers, and Fc is given. The value of Fc is 7.2 megahertz. So this is the data given, and we need to find out the value of F MUF here. So F MUF is equal to Fc into root of D by 2H whole square plus 1 here. So what is Fc given? It is 7.2 into 10 power 6 divided by the value of D is 1200. The value of H is 200. 2 into 200 whole square plus 1. So this you simplify, you will get 22.7 megahertz. You will get 22.7 megahertz. And the angle of takeoff, it is given as, this is the transmitting angle. Let us assume as beta here. And if you assume this as angle A, this is B and D. So here, tan beta is equal to opposite theta H by D by 2 here. The distance, the skip distance is D here. Exactly at the center 90, we are taking a D by 2 here. So from this triangle, you will get 2H by D here. And H value is given and D value is given. If you simplify, you will get 18.43 degrees. A transmitting antenna mounted at a height of 120 meters radiates 15 kilometers of power, equal in all directions. Calculate maximum LOS range, field strength. So here the LOS strength is nothing but D is equal to 4.12 into root HT plus root HR, the formula. So if we substitute this 4.12 into root of HT, it is 120, and it is 16 here. So if you simplify, you will get 61.61 kilometers. This is the value of D. This is the value of D here. And similarly, you can also find out the value of electric field strength received is equal to 88 root P HT HR by lambda D square. So all the data is given in the problem here. The amount of power is given as this is 15 kilowatts. So substitute here. So 88 root 15,000 kilowatts, 120 into 6 divided by 6 into 12,000 whole square. So this is equal to 23.95 millivolts. 23.95 millivolts here. This is the range of space wave propagation and the field strength of the receiving antenna, 23.95 millivolts here. Calculate the attenuation to a frequency of 600 megahertz when the distance between the transmitting and receiving antenna is 400 kilometers and gains are 20 dB. So here the spatial path loss is given by the equation 32.45 plus 20 log D plus 20 log F kilometers, and the D is given as 40 kilometers here, and F is given as 600 megahertz. You substitute this both values here, you will get 120.056 dB here. Now what is the attenuation? So the attenuation is given by PR by PT is equal to GT plus GR minus LS. The gains of the transmitting and receiving is given as 20 here in the problem, and the spatial path loss is given, we have calculated just now as minus 120, and we are getting the PR by PT, the loss of attenuation is minus 80 dB. So there will be a loss between the transmitting and receiving antenna at a rate of 80 dB. The minus value indicates that there is a attenuation loss of 80 dB. Find the skip distance when the angle of incidence is 200 and the virtual height is 50 kilometers. So we are having the formula D skip is equal to 2H in root of F MUF by Fc whole square minus 1. And here F MUF is equal to, we know that secant pi I and Fc, substitute this here. You will get secant pi I Fc by Fc whole square. So Fc get cancelled. And pi I it is given here. It is pi I this 20 degrees, substitute this 20 degrees here, and the h value is given as 50 kilometers here. If you substitute and simplify, you will get 36.33 kilometers. 36.33 kilometers. So with this we close the session today. For references, you can refer the antennas of wave propagation by Bakshi. Also the KD Prasad antennas of wave propagation. Let us close the session today. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.